It's my favorite thing to talk about and teach, and um, they're got every class has its own little nuggets of gold in it that are just amazing things. Okay. Okay, so let's get into today's material. Not 6.3, 6.2. Let me share my screen real quick if it's not shared already. Let me end the share, and then we're going to go to this guy here. I'm going to share my notes. Okay, so go ahead and make sure you have something to pen, piece of paper, something to write down. If you have an iPad or a tablet PC, feel free to take electronic notes as well. Okay, or a Surface or any of that stuff. Okay, let's share the screen. What do I want to do? I don't think I'll need a calculator today. So I'm just gonna go to OneNote. Okay. Okay, chapter 6 is going to be on exponentials, derivatives, and integration of exponentials and logs. Again, if you don't know your exponents and you don't know your logs, I'm very sorry. That's pre-calc. I can't reteach you all of the rules. So I'm just going to assume that you all have mastered that at this point. Okay, so I'll stop saying that because it's not really nice to people's self-esteem, but it's the truth. Sometimes the truth hurts. I don't know. I don't know. My kids say that I lose tact after about 10 p.m. at night. They're like, Dad, you should really just shut up after 10 p.m. because you lose tact. And then my wife says they're wrong. She says that I never have tact. She's like, you don't ever have it, whether it's 10 p.m. or below. So, well, who knows? Who knows who's correct at this point? Okay, a function. It's a good thing I don't teach after 10 o'clock at night. Okay, a function f is called, excuse me, one-to-one. Let me get rid of this guy. One-to-one if it never takes on the same value twice. Okay, that is f of x 1 is not equal to f of x sub 2 when x1 is equal to x2, or when x1 is not equal to x2. Okay, and that's for all x. Okay, so a function is called one-to-one if it never takes on the same value. How do we talk about this in terms of domain and range? Well, one-to-one means that all domain values and all range values are unique. Okay, are unique. So how do we tell if a function is one-to-one? Well, here's a function, okay, and it is not one-to-one because if I do something called the horizontal line test, boom, it's not one-to-one. Now, it's not a function if it fails the vertical line test, but it is certainly not one-to-one if it fails the horizontal line test. Okay, now why do we care about a function being one-to-one? Well, we care about a function being one-to-one. Okay, we care about a function being one-to-one if because that allows us to get an inverse function. A function has to be one-to-one in order for us to get an inverse, And since exponentials and logs are inverse functions of each other, we want to talk about the properties of inverse functions. Okay. So, definition, next definition, let f be a one-to-one function with domain domain A and range B. Then its inverse function f inverse f to the negative 1 power. I better make that a lot nicer. F inverse has a domain B and range A, defined by F inverse of y equals x if and only if f of x is equal to y. Okay, so basically it's just saying, look, the function and its inverse swap domain and range. So f of x and f inverse of x swap domain and range. Okay, what was the domain for the original function is the range for the inverse, and what was the domain of the and what was the range of the original function is the domain of the inverse. Okay, so vice versa. Domain and range get swapped. Okay. Number 1. Find the inverse of f of x equals x cubed plus 2. Okay, so this is really the only problem. I know I just went and said, oh, we're not going to review it all. Well, this is it. This is your one review problem. Okay, enjoy it. Okay, so find the inverse of this function. Okay, so going back to algebra, how do we find the inverse of this function? Well, we switch the domain and range. Well, I'm going to write this as y equals x cubed plus 2. Okay, and then what I'm going to do is I'm going to swap the domain and range. I'm going to swap the x and the y. Okay, so x is equal to y cubed plus 2. Okay, so now what I'm going to do is solve for y. So I'm going to take x minus 2 and equal to y cubed, and let y equal the cube root of x minus 2. Now I want to talk about domain and range. What is the domain and range of my original function? What's the domain and range of the original function?
All real
you can
numbers.
Chat it. You can tell me. Yeah, all real numbers. Who is that?
Gabby.
Gabby. Thank you, Gabby. Okay, so absolutely, Gabby says that the domain and range is all real numbers, and she would be correct. This is a the domain is all real numbers. The range is also all real numbers. That my all real numbers didn't look too nice there. There we go. Okay, all real numbers. Why? Well, if we look at the x cubed, isn't that a serpentine function? Doesn't it look like a little snake, right? So we're going to be x2 up to 1, 2, and we're going to have a little serpentine here, okay, right? So there's our serpentine function, okay, of x cubed plus 2, right? And so what's the domain and range? Well, the domain can be anything I want it to be. What's the range? Well, the range can be anything I want it to be. It goes from negative infinity to infinity in the x direction, and it goes from negative infinity to infinity in the y direction. It's the same, okay? The inverse also does the exact same thing, okay? So I'm going to write this as f of x equals x cubed plus 2. And then let's look at the inverse function. Maybe I'll put the inverse function on the same grid. Okay, what's the inverse function going to look like? Well, the inverse function is going to be up 2. Okay, and it's going to look like this. Okay, and it's going to be symmetric along the line y equals x, right? Okay, and so what's the domain and range of the inverse function? Okay, f inverse of x equals cube root of x minus 2. Okay, yep, all real numbers as well, Anthony says. Perfect. Okay, so let's say the domain is all real numbers and the range is all real numbers. Now, does that make sense? Does that make sense that the domain of the original function is all real numbers and the range of our inverse is also all real numbers? Well, yeah, absolutely. Why? Because in order for it to be an inverse, what are we going to do? We're going to swap domain and range, right? Isn't that like the whole point of the properties of the inverse? Yes, it is. I ask a lot of rhetorical questions because I'm the only one that answers them. So it's all good. Okay. You're like, how are you doing today? I'm doing awesome. How are you doing? I'm doing great. Man, you are a handsome man. You know what? Thank you. You are a handsome man. Okay, anyway. Number two. When I taught high school, I said a lot of rhetorical questions too because nobody would talk to me. It was really sad. I was like, forget it. Now I have to go teach college because I had to get out of there. Boom, done. Okay, no, it was good. I taught Calc A, B, and BC for 5 or 6 years. It was fun. It was good times. Okay. Okay. Let's see what we got here. Okay, we have f of x is equal to -1. Okay, minus x, -1 minus x. Okay. We want to find its inverse. Okay. Find its inverse and graph. Okay, find its inverse and graph both functions. Okay, find its inverse and graph both functions. Let's go ahead and find its inverse. Okay, first, I would like to know what the domain and range are on the first function here. So there is a restriction on my domain, right? I cannot let the restriction on the domain is that I cannot let the thing under the square root symbol be negative. So we're going to say -1 minus x has to be greater than or equal to 0, right? And this implies what? This implies that if I toss the -1 over to the other side, right, I would get negative x is greater than or equal to 1, right? And then we're going to divide by -1, which reverses the inequality symbol, which implies that x is less than or equal to -1. So that's my domain. Okay, so my domain is x is less than or equal to -1. What about the range? Okay, if the highest value that I can have here is -1, plug -1 back in, that becomes -1 plus x. Okay. Oh, the quality is making it hard to read? Like the quality of my handwriting? Is that what you're saying? You're saying I have bad handwriting? It's okay. I don't mind. This is -1. Okay. I'm trying my best. I'm sorry, Ellie. Okay. Oh, the screen is blurry. Oh, okay. The screen is blurry. You weren't talking about my handwriting. You're saying that the screen is blurry. Okay, let me stop the share for a second, and then let me go back in and share it again. Most of the time that fixes the issue. Okay. How are we doing now? We doing any better? Okay, yes, awesome, perfect. Yeah, sometimes it gets laggy down. You know what I'm gonna also do? You guys don't really need to see my face, so I'm gonna turn off my video, which might increase my internet speed, so it doesn't get laggy like that. Is that okay? I mean, all you're going to be doing is staring at the top of my head anyway for the next hour and a half, so why do you really need to do that, right? Okay. So we've got R here, okay, and R. What's the range? What's the range going to be? If the largest value that I can have is -1, if I plug that in, negative of a negative is a +1, add that to a -1, I get 0, right? What's the square root of 0? It's 0, right? So what's the range? The range is that y is greater than or equal to 0. Does that make sense? Okay. So that's on the original function f of x. That's my domain and range. What about the inverse function here? The inverse function. Okay. The inverse function is we're gonna solve that by doing the same trick that we did before. -1 minus x, right? We're gonna say this is y equals the square root of -1 minus x, and then we're gonna say, oh, let's swap x and y. So we've got x is equal to the square root of -1 minus y. Okay, and then what I'm going to do is I'm going to square both sides here. Get rid of that square root. We're going to get -y is equal to x squared minus 1. Is that right? No, x squared plus 1. And we get y is equal to -x squared minus 1. Okay, y is equal to, so this is now my inverse function. So this is f inverse of x is equal to -x squared minus 1. Okay. Okay, so now let's look at the domain and range on this guy. Okay, so the domain and range for this guy here, okay, what's the domain going to be? What's the domain going to be? Any ideas?
All real numbers.
You would think, but you would be wrong. But thank you for taking a shot. Okay, thank you for, that was awesome. I appreciate that. What was your name? Who was that? That's
Fady.
Fady. Okay, Fady said all real numbers. Unfortunately, all real numbers is incorrect. Okay, we do have some lovely parting gifts for you, though. Okay, some rice-a-roni, I think. Okay, anyone else want to take a stab at it? Okay, Anthony says greater than or equal to 0, and Anthony would be correct. Why? Why is it greater than or equal to 0? Why is x greater than or equal to 0? Because by definition of inverse, what are we doing? Aren't we swapping domain and range? Isn't that what we're doing? Isn't that what we're saying? Hey, you know what? The domain in one is going to be the range in the other, and the range in one is going to be the domain. Okay, yeah. So then we've got the range here being y is less than or equal to -1. Okay. So now let's see how this measures up when we go to graph these. Okay. So let me do not want to do that. Is there a question? For the range, can we just write infinity 1? Sure, you can, however you want to do it. Okay, that's fine. Okay, you can put it in interval notation. You can put it in set notation. You can put it in algebraic notation. Okay, it's fine. Okay, this is algebraic notation right here. Okay, set notation would be this. Okay, the range is, you know, all elements of y such that, you know, y is less than or equal to -1. I mean, if you really want to get fancy, you can go with that as well. Okay, so however you want to do it. Okay, so let's go to our graph on this guy. Okay, so let's go to our graph, see what's happening. Okay, and because we're dealing with inverses, I'm going to draw my y equals x line. Okay, as a reference. Now let's look at f of x. Let's look at f of x here. Let's do a little table here. Let's do x, f of x, x, f inverse of x. We'll do two tables. Two tables. Okay, two tables. Okay, x, f of x, x, f inverse of x. Okay, so let's look at our original function. Our original function was this guy here. Okay, f of x equals negative square root of -1. Okay, so we're saying that the highest value that I could have there is -1. Okay, basically -1 is the highest value, and that's going to produce a 0. Okay, what about -2? What would happen if I plugged in -2? What's going to happen there? Anybody know? What's f of x? It would be 1. Very good. Thank you. Okay, it would be 1. Absolutely. What about, let's do -5. What about -5? What would that be?
2.
2. You guys are amazing. Okay, I mean, it's just 0, 1, 2. Good answers. Okay, so if we went out here 1, 2, 3, 4, 5, and we went up 1, 2, then we're going to have -1, 0 is going to be a point. We're going to have -2, 1 is going to be a point, and -5, 2 is going to be a point, and we're going to get a graph that looks like that, right? That's our standard square root graph. It just is going in the opposite direction, and it's starting at, well, -1. Okay, does that make sense? So far, so good? Okay, let's look at our inverse function. What do you think our inverse function is going to look like? Any ideas? How about a mirror image? Wouldn't it be a mirror image of this thing along the line y equals x?
Yeah.
Okay. Yeah, it'll be the exact opposite, a mirror image along the line y equals x. So, you know, maybe this is, you know, we could think of this as like an airplane. I don't know. Maybe an airplane. My daughter's the artist. I'm not an artist. Okay. But if we had the fuselage, I don't know, of an airplane, blah, blah, blah. Okay, but whatever. Okay, so we would have a wing of the airplane. Boom. Okay, we have the wing of the airplane out this way. Wouldn't we need another wing of the airplane on the other? Well, let's see what happens. Okay, maybe we can create another wing here for this function. Okay, let's look at this function, the inverse function, and what did we say that we could have as our domain? Well, we can only have non-negative values, right? We can only have non-negative values here. X is greater than or equal to 0. So let's start with 0. What happens to this guy? Well, it's -1, right? So 0, -1. Okay, maybe we'll do this one in red. Okay, so 0, -1. Okay, where's 0, -1? Oh yeah, it's right there. Okay, what would happen if I did 1? If I plug in 1? Okay, then what do I get? Well, I get -2. Okay, that's interesting. Okay, and so then I'm at 1. Okay, -2. Oh, okay, like that. Okay, and then what about if I'm at 2? Okay, then I'm at -5. Oh, that's interesting. Notice that the domain and the range have swapped. Okay, notice that my inputs and outputs have swapped. Oh, that's okay. 1, 2, 3, 4, 5. And then we're going to go down to 2 here, and we're going to draw the other part, the other wing of our airplane. Does that make sense? Okay. So far so good. Wow, we went through, you guys are amazing, because we just went through all of algebra and pre-cal all in the span of about 20 minutes. That is amazing. That is just awesome. You ready for some calculus? Just go with it. Just say yes. Just take the leap. Okay, let's do some calculus now. Okay, yay, good, awesome. Thank you for playing. Okay, good. We're ready. We're ready for the calculus. Bring on the math. Woohoo. Okay, so we've got F inverse. This is our first theorem. Let's make it a theorem. Okay, let's make it, it's whenever it says theorem, you're like, you have kind of like, give it some respect, right? Like I've earned this. I've earned this respect to be called a theorem. It's almost like I want to dress up in a nice shirt whenever I see a theorem. Okay, just show it some respect. Okay, theorem. F inverse of A, okay, a function, the inverse of a function evaluated at A, that's what this is. But we're going to now take the derivative of this thing. Okay, that's what that prime there means. Okay, take the derivative, first derivative. We're going to take the first derivative of F inverse of A, and we're going to say that that is equal to 1 over the derivative of the original function evaluated for the inverse at A. That's a mouthful, right? We're saying that the derivative of the inverse is equal to the reciprocal of the derivative of the original function evaluated for the inverse at A. Whew, that is a lot to take in. Okay, let's do an example so that we can take this all in. If f of x is equal to 2x plus the cosine of x, find f inverse derivative of A. Find the derivative of f inverse. Okay, so you're like, actually not of A, let's do it of 1. Let's do it of 1 here. Okay, let's make it a value. Okay. Okay, so we want the input. Okay, we want the input. Let's think about domain and range here. We have domain and range of our original function, and then we have domain and range of our inverse function, right? So we want the input of our function to be 1 in our inverse. Does that make sense? We want the input to be 1, right? I mean, that's what A is. A is the input of the inverse function. That's this thing right here. We're inputting that value into the inverse function. That's what A is. A is our input, our domain, in the inverse function. So if we want the domain to be 1, then what does that tell me about the original function? Anybody? Say it again.
Range is 1.
The range would be 1, right? The range would be 1. Very, very good. Who is that? Okay, Anthony got it. Who else said that the range was 1? Okay, that's okay. You don't have to admit it. With me. Okay, who's that? No, yes? Okay, whatever. Okay, so the range would be 1 here. Now, what value is going to get me 1 for the range in this original function? What value would get me 1? Any ideas? I mean, we could go through all of the algebra to figure that out, right? The output should be 1. 1 equals 2x plus cosine x, right? But what's going to get me 1 here? Just take a stab at the dark. What would get me 1? Well, what's the cosine of what value is 1?
0.
0, exactly. So if I plugged a 0 in here, wouldn't that go to 0? And then wouldn't that go to 1? So if the domain of the original function was 0, isn't that going to give me a range of 1? Yes. You're amazing. I know. Okay. You guys are going to become amazing too. I just know it. Okay. And so if the domain of the original function was 0, then isn't the range of the inverse going to be 0? Does that make sense? Okay. So I know exactly what I need to do. Okay. Here's the deal. Okay. I'm going to say, okay, we want to find, we're going to do this. F of 0 is equal to 2 times 0 plus cosine of 0. And that is equal to 1. Make sense? Hopefully it does. Okay. Let's take the derivative of f. Okay, f, because eventually I need to plug in the inverse of a. But what did we find the inverse of a was? What was the inverse evaluated at 1? What is f inverse of 1? What does that equal? What did we find out that that equaled? What was the range for f inverse? What was the output? 0. Is 0, exactly. Very good. Okay, so now this is what we want to do. We're going to take our theorem and we're going to say that f inverse prime of 1 is equal to 1 over f prime of f inverse of 1, which is equal to 1 over f prime of 0, right? And so all I have to do is figure out what f prime of 0 is. Well, that's not too tough. If f of x is equal to 2x plus cosine x, then what's the derivative of f? What's the derivative of f going to be? Anybody?
2 plus sine x? Or 2
Close,
plus
very close.
2 minus.
Yes, you want? Very good. You knew you guys would get there. That was a team effort right there. She's like, no, you're wrong. I got it. Okay. Yes, absolutely. It is 2 minus sine x. Very good. Okay, and so what's this going to be? If I evaluate this, okay, at 0, f prime of 0 is equal to what? Well, that's 2 minus the sine of 0, which is 2. Oh, that's cool. So what's the f prime of 0 going to be? Isn't that going to be 2? Yeah. And so what does this end up being? 1/2. Boom, there's my answer. Easy, peasy, breezy, squeezy, however you want to, whatever rhymes with sleazy. I don't know. Okay. It's easy. It's easy stuff. Okay. Okay. You ready to move on? Get on to some good stuff. That's just inverses. Okay, we're gonna do 6.2 now. Okay, 6.2 star. Again, these are the blue pages in the book. The blue pages in the book. Okay. Okay, definition. Again, if you have questions, please let me know. I'll slow down. Okay, or if you're having a hard time catching up with the writing, I'll slow down as well. Okay, if you have questions, please let me know. Okay, the natural log function Okay, the natural log function is defined by natural log x equals the integral of 1 over x times 1 over t dt for positive x. Okay, for positive x. That's how we are going to define in calculus the natural log function. You've probably seen it defined other ways, okay, in other classes, but in calculus, this is how we're going to define the natural log function. Okay, it is the integral of 1 to x of 1 over t dt. What does that mean? It means that if I had, okay, an axis here with t on it, and I had the function f of t equals 1 over t, okay, and that's my hyperbolic rational function here. It's a hyperbola, okay. It also has a mirror image in the third quadrant, but that's okay. I don't need to bother with him because we're only, why do we not need to borrow? Because we're only dealing with positive x's. I'm saying we're going from 1, okay, we're going from 1 to x. Okay, going from 1 to x, and we're saying that the natural log of x is equal to the area under the 1 over t curve from 1 to x. Okay, that's the calculus definition of natural log. This area under the curve here, that's the natural log. That's pretty cool. That's some cool stuff right there. I don't know why everybody just doesn't take Calc 2. Okay, this is some sweet math right here. Okay, the natural log function is defined by natural log x equals 1 to x of 1 over t dt. X is greater than 0. Okay, so the area under the 1 over t curve from 1 to x is the natural log function. That's how we define it. It is that. Okay. If we use the fundamental theorem of calculus and we want to take the derivative with respect to the integral, it's kind of interesting. The derivative of natural log, okay, that's going to be equal to d dx of 1 to x of 1 over t dt. Okay, that is equal to 1 over x. Okay, why? By the fundamental theorem of calculus. Okay. So if we take the derivative of the integral, we get 1 over x. We get the rational function of x. Okay. Now, why is that important? Well, it's important because we're going to start taking derivatives of logs. That's why it's important. The derivative of a natural log is 1 over x. Okay, so keep that in mind. Okay, d dx of the natural log of u of x is equal to 1 over u times u prime, which is equal to u prime over u. And this is the chain rule, right? By the chain rule. Why can we use the chain rule? Because u is a function of x. That's why. Okay. You could have, I could have put f there if I really wanted to, f of x. It really doesn't matter. Okay. But I'm going to use the chain rule here. Okay. For u. It's just kind of like, think of a u sub on that one. Okay. Definition. Okay. Let's do a definition here. Okay. Definition. Okay. E is defined as the number such that the natural log of E is equal to 1. Okay, we're going to define e as the number such that when I take the natural log of e, I get 1. That just tells me that the natural log and the natural exponent are inverse functions. Ln x and e to the x are inverse functions. They undo each other. It's like adding 2 and subtracting 2. They undo each other. Okay. I forgot an r there. Inverse functions. Okay. They undo each other. Undo each other. Okay. Okay, we good? We good so far? Ready to do some calculus? Ready to jump in with both feet now? Okay, let's do some logarithmic calculus. Number 1, let's differentiate y equals the natural log of x cubed plus 1. Okay, let's take the derivative of this thing, right? So this is a chain rule. This is a chain rule. So what's y prime going to be equal to? Okay, well, we're going to have to take the derivative of natural log. But what is the derivative of natural log? Isn't it just 1 over x, right? But here we have a 1 over this thing. So if we go back to our chain rule, by the chain rule, it's going to be 1 over the original function times the derivative of the function, right? Oh, okay. So this is going to be 1 over the original function times the derivative of the original function. And so this is going to be equal to 3x squared over x cubed plus 1. Okay. Good. So far, so good. Okay, let's see what we got here. Number two, let's take the derivative of, of the natural log of sine x. Whew. Let's take the derivative of a natural log of sine x. You're like, he's already throwing trig stuff. We're already doing logs and exponentials and trig all in the first day. Yep, that's how we roll, baby. Okay. School's in session, and someone's going to be taught a lesson. That's all I have to say. Okay. Oops. Sorry, my screen just went black. That's what I get for speaking. Stop the speaky speaks. Let's get out of the blackness of the screen. Come on, come on, come on. Okay, am I back? Am I back? I think I'm back. Okay, please move. I think we're good. Gosh, I did it again. This is not good. I keep doing. Come on, come on, come on, come on. Okay. There we go. I think I'm back. Am I back? Okay. Okay. Is the screen blurry again or no? Can you see the screen?
It's
Is
a
it blurry
little
again?
blurry, like a little bit, yeah.
It's a little blurry? Okay, let me stop
Yes.
the share again and we'll go back into the screen share. Sounds good. Hopefully that's better. Is that better?
Yeah, that's better.
Yeah.
Okay, perfect. Okay, so let's take the derivative of natural log of sine x. Okay, we're going to combine the natural log with the trigonometric function here. Okay, and so we're going to say, well, what's this going to be? This is going to be, okay, 1 over sine times the derivative of sine. And what's the derivative of sine? Well, derivative of sine is cosine, right? And so we're going to go cosine over sine, which is equal to cotangent x. Oh, okay, that's cool. Okay, number 3. Okay, f of x is equal to the square root of natural log of x. Okay, let's take a look at this one real quick. F of x is equal to the natural log, the square root of natural log of x. Okay, so let's take the derivative. Let's use chain rule here, right? Chain rule, derivative of the outside. Okay, what's the derivative of square root? Well, it's 1 over 2 square root, right? Does that make sense? It's 1 over 2 square root. And if you don't know how I did that, you can prove it to yourself later. Okay, that's natural log of x, right? Just change it to an exponential function. Okay, and you get 1/2, bring the 1/2 down, and it becomes like that. Okay, 1 over 2 radical ln x. Okay, times the derivative of the inside. Well, what's the derivative of the inside? The inside is natural log of x. Derivative of natural log of x, we already saw what that was. By definition, it's 1 over x. So we're going to get 1 over 2x square root of natural log x. Okay, does that make sense? Natural log x to the 1/2 power. 1/2 natural log x to the negative 1/2 power, right? Times 1 over x. Same thing. All good? Okay. Okay. Number 4. Okay, let's take the derivative of the natural log of x plus 1 over x, the square root of x minus 2. Ooh, this looks fun. Any ideas on this one? Any ideas on how to approach this? Any ideas at all?
Quotient rule?
Quotient rule. Yeah, quotient rule. No, but no, that's what you would think, right? You would think it's quotient rule. You would think, oh man, I want to use quotient rule here. And no, because quotient rule is going to be a beast, right? It's going to be a bear to do quotient rule on this thing. You really want to take derivative top, derivative bottom, minus, derivative of the top minus times the bottom minus derivative of bottom times the top, all over the bottom squared. You could do that if you really wanted to, but then we have to take a natural log of the entire thing, and that's not going to be fun. It's not going to be fun here. Okay, so in order to avoid the quotient rule at all cost, avoid the quotient rule, we're going to use properties of logs. Somebody already put that in here? Okay, use log rules. Thank you, Ebony. I'm so glad that you're a part of the class, that you made it. Okay, shh. See, she knows what she's talking about. That's good. Okay, Ebony says use log rules. Okay, specifically, what are we going to use for the log rules? Okay, natural log of x plus 1 minus the natural log of the square root of x minus 2. Psh, nice. Now I sound like John Krasinski. Nice. Okay, natural log of x plus 1 minus natural log of the square root of x minus 2. Okay, and we're going to take the derivative of that. Well, what's the derivative of natural log of x plus 1? Isn't that 1 over x plus 1 times the derivative of x plus 1, which is 1? minus, what's this one going to be? 1 over the square root of x minus 2 times the derivative of the square root of x minus 2. Okay, that's 1 over 2 square root x minus 2 times the derivative of x minus 2. It's a chain rule inside of a chain rule. It's chain rule inception. Okay. How many levels down do we want to go? Okay, 3 in this case. Okay, so times the derivative of x minus 2. What's the derivative of x minus 2? 1, right? So what does this become? It becomes 1 over x plus 1 minus 1 over 2 times x minus 2. Okay, and I can leave it like that if I really wanted to. I could multiply it out. It really doesn't matter. Okay, you can leave it in factored form if you want. Or you can do the extra work of doing 2x minus 4, and we're done. At that point, I don't want to create a common denominator because that's too much work for me, and I'm lazy. So, no, I'm just kidding. Because I don't get a return on the investment, that's why. Okay, a lot of people don't understand this about math, that math is symbolic logic. Okay, math is symbolic logic. And what does it mean to simplify something? When your teachers asked you all these times, simplify, simplify, simplify your expressions. What does that mean? What does it mean to simplify? Okay, as a mathematical term, what does it mean to simplify? It really comes down to this. It means write the exact same thing or value with less symbols. Okay, if I say that 3x plus 5x plus 7x, and I want to simplify that, what does that mean? It means that give me the exact same meaning, but with less symbols. That's all it means. Okay, and if you end up multiplying that thing together, finding a common denominator, is that really simpler? The heck? Sorry, is that really simpler? I don't know why. It's not simpler. Okay, where you have to consider how many symbols you're writing. Right? Does it have the same meaning, and are you using less symbols to write that? That's the idea there. Okay. Come on, let's go back to my screen sharing. Okay, so is 3x plus 5x plus, we said 7x, okay, which is 15x, right? This guy here, 15x, how many symbols does that have? 1, 2, 3, 3 symbols. Okay, how many symbols does this guy have up here? 1, 2, 3, 4, 5, 6, 7, 8 symbols. Do they mean the exact same thing? Absolutely. Do they have the exact same purpose in math? Absolutely. Which one is easier to write? 15x, okay? It has 3 symbols as opposed to 8. Okay, so when we ask to simplify something in mathematics, it means give me the exact same meaning, but with less characters. Okay, less characters. Okay. That one you guys get for free. Okay, that's not part of the class. Okay, will not be on the test. Okay. But for some reason that eludes a lot of the problem is, and I don't mean to discount any educator who is trying to teach third graders math. Heaven help them. And I understand why they have a limited point of view in the way that they teach it, but you know, some of these lessons get lost along the way. Okay. You know, the why we do something is sometimes better than the how we do it. And in this class, I would really want you to learn the well, we're on number 5 here. Learn the why. Why are we doing this? Why are we doing this? You know, why is more important than how. Okay. If I know how to drive a car, that's less important as why that car drives the way it does. Right? Why is more important than how. Okay, I could sit here and teach you how to do a problem all day long, and all I'm doing is training a robot to spit out a certain answer. But that's not going to help you build a bridge or fix a computer software problem or anything like that, or, you know, calculate the trajectory of a rocket. Okay, that's not going to help you do any of that stuff. Just to sit here and make you, you know, go over and over and over and over a certain problem. Okay, but if you can learn why you're doing something, that's much more powerful. Okay, why are we doing this? What's the point? Okay, number 5, find f prime of x if f of x is equal to the natural log of the absolute value of x. And this guy here, this problem here goes to the essence of why. I'm going to talk about what the answer to this problem is and why it is so important in calculus. This is an extremely important problem in calculus. It's the reason that we have these absolute value bars here. And people are always like, well, why do you put the absolute value bars there? Why do you put the absolute? Well, because my teacher told me to. Because my Calc 1 teacher told me to put absolute value bars there when I integrate. I'm like, well, why do you do that? They have no idea, no clue. They're just like, well, somebody told me to do it, and I did it, and I always got the right answer. Bravo. More power to you. But we're not going to do that in this class. Everything that we do in mathematics has a reason why. And in this class, hopefully you will learn the reason why. Okay, the why is more important than the how. Find f prime of x if f of x is equal to natural log of absolute value of x. Okay, so what is the absolute value of x? Okay, how would I define the absolute value of x? You know, even as just a function. Okay, the absolute value of x, that's this little v function, right? Okay, again, we'll do a little pre-cal here. Okay, it's a little v function. Okay, and what is this function really a function of? It's really a function of two functions. It's a function of two functions. It's what we call a piecewise function, and it says that f of x equals absolute value of x is, okay, absolute value of x is x, it's the line x, maybe I'll put this in color, okay, color it up, is x when x is greater than 0. Oh, okay. When x is greater than 0, then it is the line x. Okay, but it also is negative x. It also is negative x when x is less than 0. Okay. Okay, so when it's less than 0, it's a negative line. It's a negative slope of -1, right? So that's what that means. Okay, so what is this function natural log of absolute value of x mean? Well, f of x equals ln of absolute value of x. That means that it's the natural log of x, okay, if x is greater than 0, or it's the natural log of negative x if x is less than 0, right? Does that make sense? Okay. And we're not going to talk about what happens at 0. You could have, for the original function, you could have it either the greater than or the less than. For the natural log, you cannot take the natural log of 0, so we don't include it. Okay, natural logs cannot equal, you cannot take the natural log of 0. Okay, natural log of 0 does not exist. Okay, so you can't take the natural log of 0. Okay, so, because it's an asymptote. Okay, don't take the natural log of 0. You're going to make an asymptote out of yourself. Okay, just letting you know. Okay, just don't do it. Okay, put the natural log down. Okay, put the pun. Oh yes, thank you, Jamson. Thank you. The puns are for free as well. You don't have to pay for the puns. They're free as well. Okay. Okay. So just the calculus. Okay. Let's take the derivative of this guy. Okay, let's take the derivative of this guy. F prime of x is equal to what? What's the derivative of natural log of x? Everybody should know that at this point, right? Put it in the chat box. What's the derivative of natural log of x? Okay. 1, 2, 3. Everybody's just going to copy. After like the first 3, people are like, oh, what did they put? Oh, I agree. It's one of our. You guys are amazing. You guys are geniuses. You're geniuses. Okay. Martin, genius. Okay. With a name like Martin, you got to be a genius. Okay. So natural log, that's 1 over x. It's 1 over x if, okay, if x is greater than 0. If it's positive, x is greater than 0. Whew, nice. Okay, what about the derivative of natural log of absolute value if x is less than 0? I'm going to close this because it's getting warm in here. Okay. Okay. In summer. Okay, so what is the derivative of natural log of negative x? What's the derivative of natural log of negative x?
1 over negative x times negative 1.
Very good. Who is that?
Fatty.
Fatty, very good. Good, great job. Okay, it's 1 over x, 1 over negative x times negative 1, which is what?
1 over x.
Exactly, it's just 1 over x. If x is greater than 0, right? Okay, what does that tell me? That tells me that the derivative of the natural log of absolute value of x is equal to what?
1 over x.
You know what? I like it. Okay.
Sorry, I have a question.
Yes, absolutely.
Is it is it 1 over negative x because you need to factor out the negative 1?
Well, we're using the chain rule, right?
Yeah. Oh, okay.
So we're saying that it's the natural log of negative x, right? And so we put that 1 over negative x first, right? Because it's always 1 over the original function times the derivative of negative x, which is negative 1. So it makes it positive. Does that make sense?
Yeah, okay, thank you.
Okay, yeah, absolutely. And that's why this is so powerful, because what happens is all roads lead to 1 over x. Isn't that kind of cool? It's kind of cool that if we have 1 over x and we just make it the natural log of an absolute value, we don't have to deal with these 2 different outcomes. We only have to deal with one outcome. The one outcome is 1 over x. Now, what's even cooler about this, okay, here's the real cool stuff, okay, is that when I take the integral of 1 over x, right, when I do the antiderivative of 1 over x, what is that going to become? What's the antiderivative of 1 over x? If all roads in one direction lead to 1 over x, then shouldn't all roads in the opposite direction lead backwards to natural log of x?
With natural log of x.
Absolute, yeah, but don't forget the absolute value, right?
Yeah, yeah.
Exactly. Natural log of absolute value of x plus c. Always plus c, okay? Always plus c. It's like Mr. Miyagi in the Karate Kid. That's a dated reference. I'm dating myself, but that's because nobody else will. But anyway, so it's Mr. Miyagi, right? So when Mr. Miyagi is training Daniel, right? Karate Kid, Cobra Kai, woohoo, yeah, okay, and he's like wax on, wax off, right? And he says he goes in, he's like, oh, wax on, wax off. He says, no, wax on, wax off. Paint the fence. Show me paint the fence. He's like, paint the fence, paint the fence. Up, down, up, down. He's like, smack you in the face. No. He's like, and he says, look eye, always look eye. It's a sign of respect, right? In Japanese culture. Guys from Okinawa. Okay, so he said, look eye, always look eye. Well, it's plus C. Always plus C. Always plus C. Don't forget it. Always plus C. Anyway, I digress. Okay. Always plus C. Don't forget the plus C. Okay, let's do number 6. Okay, we got nine problems to get through, and we're only on number 6. So let's move it. Got to move it. Got to move it. Okay, King Julian would be proud. Okay, x over x squared plus 1 dx. Okay, x over x squared plus 1. Let's take the integral of this guy. Okay, what are we going to do on this? Any ideas? First step? Do some integration? Yeah? Any ideas?
I would use U substitution.
Yeah, absolutely. Who's that?
Ebony?
Ebony. Thank you, Ebony. Absolutely. And Ebony, are you go to Cerritos, or are you from another college?
I'm just happy to be here
Okay, good.
for the summer.
What college do you normally attend?
I'm actually a math teacher.
Oh, you're a math teacher. That's right. Okay. Yes.
I miss calculus.
Oh, so you probably know some good math jokes too. So feel free to share.
Oh,
Okay.
always. I'm telling the jokes.
Always. Yeah, exactly. So that's how I keep my students awake. They're like, that was actually a survival skill when I was teaching high school. Like, they're like, Mr. Holman is so funny. I'm like, that's because I was so scared of them, because they were like, I'm very small, 5'6", and that was my only survival mechanism, was to tell them jokes. And then they were like, hey, you be quiet in that guy's class, because he's funny. So if you want the funny, you do what you're told. And then they would be quiet, and I'd be able to teach my little numbers. So it was a good strategy there. It worked well. Okay. Exactly. You gotta do whatever works, right? Whatever works. Okay. Okay, so u, okay, is equal to x squared plus 1. So we're going to do a u sub on this, just as Ebony suggested. Okay, and we're going to do du is equal to 2x dx, right? Okay, so now I'm going to divide by 2. Okay, and we're going to get du over 2 is equal to x dx. Okay, and I'm going to isolate the x dx because I want to do a u sub on this. Okay, so let's do that. Let's go integral, okay, of 1 over u. Okay, why that? Because the x squared plus 1 is in the bottom. So x squared plus 1 is in the bottom. We're going to go 1 over u times, okay, du over 2, right? So I could pull the 1/2 out if I really wanted to. I don't really need to at this point. Okay, so what is this going to, what is this going to get me? Okay, this is going to get me natural log, right? If I take the integration, natural log, and this is 1/2 natural log, okay, of, nope, that's not, is that right? Yeah. So integral 1/u is natural log, that's correct. Okay, 1/2 natural log of absolute value u. Okay, so absolute value u, right? The integral of 1/u is the 1/2 natural log of the absolute value of u. Okay, plus c. Don't forget the plus c. Always plus c. Always plus c. Okay, always okay. Okay, always plus c. Okay, if you have an indefinite integral, always plus c. So now I could change this, okay, back to my original function, okay, for u, which is 1/2 natural log of x squared plus 1, okay, plus c. Okay, and then I'm going to use the property of logs here to make this natural log of the square root of the absolute value of x squared plus 1. And I don't think that I can undo that absolute value unless I were to, well, can I? Can I undo the absolute value? Am I allowed to do the undo the absolute value? Is there any value that's going to be a problem? No, because that x is being squared, right? Isn't the x being squared? That's great. X squared plus 1 is what? Always greater than or equal to 1. So it will never be negative, right? That will never be negative, which means that I can remove the absolute value bars. Well, that's kind of cool. There we go.
I need to put I mean, like, to make the half as the what was it called, the square root?
The square root?
Yeah.
Yeah, I would prefer that. Again, it's much better to write this with 1 symbol instead of 3. Does that make sense?
Yeah, because as I remember from my high school, I didn't need to do it. He was like, all right, that's fine. I'm just asking.
Because I mean, mathematicians are, you know, they're hard workers, but they're lazy too. They don't want to write more symbols than they have to, right? Why would you write more symbols than you have to? I don't want to do that. Okay, so a square root symbol is a lot easier to write than the 1/2. It's less symbols. Okay, especially when you had to, back in the day, you know, 300, 400 years ago, you had to write this stuff out letter by letter by letter by letter. You know, you didn't have the technology that came around, you know. Even the printing press, you know, we were doing mathematics way before the printing press. And so if you wanted to write a math book and then rewrite it, you'd have to rewrite that thing letter by letter by letter. So why would you want to carry extra symbols with you if you didn't have to? Don't get rid of that baggage. Let it go. Okay? Let it go. Let it go. Don't hold me back anymore. Okay, whatever. Okay. Let's do number 7 here. Okay, let's do number 7.
Can you scroll up, Professor, quickly?
Scroll up. Oh, what does that mean, scroll up? What does it mean to scroll up? Did I lose you?
The notes above what's being shared.
Say that one more time. You're cutting in and out.
I think it's so you can see the full problem.
Oh, so you can see the full problem. Again, this will all be posted on YouTube. I mean, I can do it here. It will all be posted on YouTube in an hour. So if you have to go back, if you accidentally miss something, you can always go back. This is all going to be recorded. Okay. Not that, you know, I won't stop and pause. It's fine. I can stop and pause, you know, as much as you want. But just keep in mind, if you do miss something and you're like, oh man, that was 2 problems ago and I missed it, it will all be recorded and uploaded on our playlist on YouTube, okay? So just to let you know. So you're never going to miss something in this class. Okay, you'll have access to all of it. Okay, calculate. Okay, calculate. Okay, let's do the integral of 1 to e of the natural log of x over x dx. Okay, natural log of x over x dx. Okay, u sub on this one. What do you think the u sub is going to be? What's the u substitution going to be? U equals what? Ideas?
Natural log of x,
Natural log of x. Yeah, why? Why would we want to go with natural log of x here?
because we can simplify the natural log of x to something like more simpler. So we can substitute.
No, not yeah, not really. What's the derivative of natural log of x?
1 over x.
1 over x. And do you see how we have an x in the denominator here? And so this is kind of like 1 over x dx, right? And so can you see how this is now my du?
Mm-hmm.
And the natural log is my u?
Yeah.
That's pretty sweet. That works. That's awesome. Okay, so let's do the u sub. Well, we don't have an indefinite integral here. We have a definite one with limits. So let's do u of e is equal to the natural log of e. What do we say the natural log of e was? By definition, the natural log of e is?
1.
1.
1. Very good. Very good. You should have that in your notes. Okay. And then what's the natural log of 1? What's the natural log of 1?
1. 0 no, doesn't
Nope,
exist.
it's not.
Doesn't exist.
It does exist.
It does.
It does exist. It's 0. Yeah. You got to know your logs, people. Got to know your logs. Okay. Okay, that's your homework, is to review all those properties of logs. Okay. Okay, why is the natural log of 1 0? Well, if you memorize what the natural log looks like, it looks like that. Right? And so when we're at 1, where are we? Where's the function? Isn't it the x-intercept? Right? Does that make sense?
Yeah.
Okay, awesome. Very good. Okay, so we're going to change our limits of integration from 1 to e to 0 to 1. And then we're just going to have u. Okay, u du. Oh, wow, that's so simple. Okay, that's so simple your grandma could do it. Well, maybe not your grandma. Maybe my grandma. My grandma can't do it anymore because she's not around anymore. But maybe she could do it if she was still alive. What is this guy going to be? U squared over 2 from 0 to 1. 1/2 minus 0 is 1/2. That was simple. That was way too simple for you people. Okay, I don't even know why I put it up as a problem. I apologize. I apologize for putting that problem up there and insulting your intelligence. That I apologize for. Way too simple of a problem. Okay, let's go to number 8, shall we? Oh yes, we shall. Okay, the integral of tangent of x dx. Okay, the integral of tangent of x dx. Interesting. Okay. Now, we could certainly look this up in a table of integrals if we really wanted to. But what's the fun in that? There's no fun in that. Looking it up, let's derive it by hand. That's the fun. There, look it up in the table of integrals. I scoff at you. I laugh in your general direction. Okay, let's do this by hand. What is tangent? Tangent is sine over cosine, right? Isn't tangent sine over cosine? Dx, okay. So we're going to do a u sub on this. U is equal to, I'm going to do the cosine of x this time. Okay, do the cosine of x. Okay, because I want to get that sine to be in the denominator. I want that to be my du. I want to get this to be 1 over cosine x times sine dx. I want the sine function to be my du. I want that to be du. Okay. So what is du in this case? Well, du is negative sine x. And so negative du, okay, is equal to sine x dx. Okay. So that was a negative du. Okay, so this is really equal to 1 over u, negative du. Okay, so I'll put the negative 1 there. That helps. Okay, so now what is the integral of this? Well, isn't that just negative natural log of u plus c? Yeah. It's kind of cool. Okay, let's use property of logs here to simplify this guy. So this is the natural log of the absolute value of u to the negative first power. Okay, plus c. Okay. Well, isn't that the natural log of 1 over the absolute value of u plus c? Isn't that what that is? Yep. Okay, and then what was u though? Wasn't that cosine of x? So this is going to be natural log of 1 over the absolute value of cosine of x plus c. Okay, which is the natural log of the absolute value of secant of x plus c. Nice. And that's it. That's the answer. This is equal to the derivative of tangent of x. No, I'm sorry, the integral of tangent of x. Not derivative. Derivative of tangent of x is tangent secant. Or secant squared, sorry. So this is the integral. So the integral of tangent of x is equal to this guy. Okay, last problem. We ready for our last problem? Woohoo. Last problem. Okay, any questions up to this point? We good?
I have a question, Professor.
Yeah, absolutely.
It's from number 7. I just didn't want to cut you off.
Okay, no, go ahead.
Is it okay to ask you? All right.
Yeah,
So
sure. Please.
You changed the integration from 1 to the x to 0 to the 1. I don't actually remember why did we do that.
Okay, so because we had limits of integration, right? We had to change. We're changing what we're taking the integration of. We're integrating with respect to u, right?
Yeah.
For our du, right? We're integrating with respect to u, and so we have to plug this in.
Yeah, got it. Got it.
Okay,
right,
sounds good.
you.
Sure, absolutely. Yeah, anytime. Okay.
Thanks.
Any other questions on anything up to this point? Okay, we're going to go into our last problem. It's a big one. Okay, so I don't want anybody to be confused going in. Okay. Okay, number 9. Let's do number 9 here. Number 9, last question. Let's find y prime. Okay, let's differentiate. Okay, differentiate. Y equals x to the 3/4 times the square root of x squared plus 1 all over 3x plus 2 to the 5th power. Okay. Okay, so we want to differentiate this guy. And what we're going to use is we're going to do something called logarithmic differentiation. We're going to use logarithmic differentiation. Okay, and the way that we do that is we take the natural log of both sides. And what that allows us to do is it allows us to write this rational expression, this really kind of scary rational expression. Oh, it's blurry again, okay. Okay. Okay, and so what we're going to do is we're going to use the properties of logs here to break this up. So we're going to go natural log y is equal to the natural log of x to the 3/4 plus the natural log, I'm going to write this as x squared plus 1 to the 1/2 minus, excuse me, natural log of 3x plus 2 to the 5th power. Okay, now I'm going to put these exponents in front. So this is going to be equal to natural log y equals 3/4 natural log x plus 1/2 natural log of x squared plus 1 minus 5 natural log 3x plus 2. Okay. Okay. So now let's take the derivative of this thing, okay, in pieces. So what would be the natural log of y? Remember, this is like u. This is y is a function of x. So that would be 1 over y times y prime. Okay, that's implicit differentiation. We're doing implicit differentiation there. Okay. Okay, implicit differentiation. Okay, and so now let's do explicit differentiation on the other side. Okay, so 3/4 natural log of x. Well, isn't that just 3/4 times 1 over x? Right? Okay, what about the next one here? This is going to be plus 1/2 times the natural, or not the natural log. We want to take the derivative of this thing. So that's 1 over x squared plus 1 times 2x. Okay, and notice the 2's cancel. It's kind of nice. Minus 5, okay, times 1 over 3x plus 2 times 3, right? Derivative of the bottom is 3. So let's clean this up. This is y prime over y is equal to 3 over 4x, okay, plus 1 over x squared plus 1 minus 15 over 3x plus 2. Okay. So now you're thinking, well, how did that help us? We have a y prime and a y now. Yeah, but we know what y is. And yeah, go ahead. Question?
For the 1 over x squared plus 1, aren't you missing an x in the numerator?
Oh, yes, thank you, I am. Yes, thank you. I did. I dropped that. Thank you very much. Okay, so yeah, the x should be in the numerator. Okay, so now what are we going to do with this y? Well, we're going to multiply the y by both sides. Okay, And then what is y prime? Well, y prime is equal to y, which is what? That was our original function, wasn't it? What was our original function? It was x to the 3/4 times the square root of x squared plus 1 all over 3x plus 2 to the 5th times 3 over 4x plus x over x squared plus 1, x over x squared plus 1, okay, minus 15 over 3x squared, or sorry, 3x plus 2. Okay, that's it. That's the derivative. Okay, and that's the last problem that I'm covering for today. Okay, make sure that you are working on the homework. I believe the first homework is due on Thursday. No, Wednesday. I don't know. Okay, I think it's due in 2 days.
About office hours. Are office hours like one,
Yes.
or is it like a group session thing?
It's a group. So I'm just gonna field questions.
So we can just like go and listen to other people's questions too.
Oh yeah, absolutely. First come, first serve. So, yeah, it's a group session. Okay, so yeah, that'll be the next time that we meet, or you'll have the opportunity to see me is tomorrow at 1:30. Okay, that'll be my first office hour.
Sir,
I'm sure it'll just be.
Can I ask you one last question? I know I ask a lot of questions, but for me, I have a question about.
Let me just.
Sorry. Just go ahead.
One second.
Yeah.
What was your question, Fady?
My question is about the inverse. I didn't really get it, so I don't like to cut you off. Like, if that bothers you, if you want me to ask you why the
No,
question
that's
is,
fine.
just-
Yeah. You can always stay after and ask me questions afterward.
Yeah. All right.
It really doesn't matter.
Okay.
Either way. So if you do not have any questions, you are dismissed. Feel free to go at this point. Okay. If you I am always available by email, and I have office hours at 1:30 tomorrow. Okay, I'll be in my virtual office tomorrow at 1:30. Make sure that you sign up on the homework. And if you have extra questions, we still do have 40 minutes left of class. So I will be sticking around and answering any questions that you have at this point in time. Okay? If you do not have any questions, you are free to go for today. Make sure that you have WebAssign and you're all good. Okay? Bye. Okay, go ahead, Fady.
Can you go over the inverse question that you did, the fx equal to x plus cosine x again, please? Thank you.
Yeah, absolutely. Okay, sure. So, sure, absolutely. Okay. So we had f inverse prime of a is equal to 1 over okay, you're very welcome. Okay, 1 over f prime of f inverse of a, right? Okay, and what we wanted was we want this. We want f inverse prime of 1.
The screen is so blurry, I cannot see you, sorry.
Oh, it's blurry again? Okay, sorry, yeah. Okay, that's fine. So let me do this. So share my screen. Okay, is that better?
Yeah, thank you.
Sure. Okay. Sure, absolutely. Thanks, Anthony. Okay, so we want this 1 over f prime, that's a prime, by the way, f prime of f inverse of 1, right? So what I'd like to do is find out, well, what's f inverse of 1, right? And they tell me that f of x is equal to 2x plus cosine x, right? And I'd really want to find out, well, what's f inverse of this of 1 without actually having to work it out, because to try to find the inverse function of this thing is going to be a real nightmare. It's a real pain. Okay, so I want to try to logically figure this out. Okay, so 2x plus cosine x, right? So I want this to be equal to 1 because, again, if you think about it this way, okay, if I go in and do my inputs and outputs, right, for my inverse, this is going to be, say, f of x, right? And this is going to be, okay, these are called function machines. Okay, you plug it in. It's like, think of it like a pizza conveyor, a pizza oven, right? The pizza comes in, and then it comes out, and it's pizza, and it's delicious. Okay, but what comes in is dough, and that is not delicious. That is just a bunch of water and flour. Okay. Okay, and so this is f inverse of x, right? Okay. Okay, so we have f of x, and we have f inverse of x. Okay, and so what was f of x? F of x was this guy. Now I want the output to be 1. Why do I want the output to be 1? Because I want the input of my original function to be, of my inverse to be 1. Right? I want my output to be 1 here, and so I want my inverse to be 1 I want my output to be 1 so that will give me my input for my inverse. Okay, and so I can say, well 2x, okay, 2x plus cosine x is equal to 1 when what? Well, I mean, I could try to solve this, or I could just start trying some values, and a real easy value to try is 0. And I can see that, oh yeah, the cosine of 0 is 1. And so 0 works. So x equals 0, okay, will give me f of x equaling 1. So if I plug in 0 here into my original function, I get out 1. And if I plug in 1 into my inverse, I should get out 0, because the domain and the range, they flip. Does that make sense?
Yeah, I understand. Yeah.
Okay. So now we say, well, we want f prime of x. What's f prime of x, right? Because we want to, what's the inverse of 1? Well, the inverse of 1 is 0, right? Is 0. The inverse of 1 is 0. So I want really f prime of 0. I want f prime of 0 in the denominator here. Okay. So I want that to be 0. So what is f prime of x? Well, f prime of x is equal to 2 minus sine x. Does that make sense? And so f prime of 0 is equal to 2 minus the sine of 0, which is 2. Okay, and so this just becomes 1 over 2. 1 over 2. That's it.
Got it. Thank you.
Okay, sure, absolutely.
So for right now, I understand everything, and thank you, and I appreciate it. And
Yeah.
I will start. It's because right now, it's because to get the web assigned, I'll have to wait till tomorrow because my dad is out of the country, and I'm waiting for him. So when he comes, he will come tomorrow. So
Okay, perfect.
I will start my doing homework tomorrow.
Awesome, perfect. Okay. Okay, see you later.
See you. Have a good day.
You too. Bye. Okay, anybody else have any questions before I end the session? Going once? Going twice? Okay, I'll see everybody tomorrow. Okay, thank you.